Okay, so this is Florence, the mathematics user. We are to look at type 2 partial fractions. Now on the board we have 3x plus 1 over x minus 1, then into bracket x squared plus 1. How do we identify that this falls under type 2? With a type 2, you have a combination of denominators, with one of them being a quadratic factor. So since we have a quadratic factor which cannot be factorized, its numerator will be written as bx plus c. You can decide to use a different variable for this b. So we know that our 3x plus 1 over x minus 1 x squared plus 1 is identical to a on x minus 1 plus bx plus c over x squared plus 1. Now this is what we do. We find the LCM here, then we obtain x minus 1, then we have x squared plus 1. So x minus 1 into this is going to give us the x squared plus 1 plus x squared into this is going to give us bx into bracket bx plus c into bracket x minus 1. Now, if we compare our denominator to this, they are the same. So we can equate the numerators. So we have 3x plus 1 is equal to a into bracket x squared plus 1 plus bx plus c, then into bracket x minus 1. We can factorize, we can expand and compare what we have on the left hand side to what we have on the right hand side. Now we have 3x plus 1 here. When we expand this, we obtain ax squared plus a. Bx times x will give us bx squared. Bx times negative 1 is negative bx. C times x is cx minus c. Then 3x plus 1, as we continue, 3x plus 1 will be equal to here. Let us factorize them according to the x. So here we have x squared, then x squared, so we put them together. So ax squared plus bx squared. Then we go to the ones with just x having an exponent of 1. We have plus cx minus bx, then plus a minus c. When we factorize, we have 3x plus 1 is equal to a plus b, then x squared, then plus into bracket c minus b, then x, plus a minus c. Okay, now we want to compare. When we check for x squared here, we do not have, so we can put 0x squared here, plus, then that's it. Then we continue. Now as we compare, we can say that our a plus b is equal to the coefficient of the x squared, which is 0. So we have a plus b being equal to 0. Then we also have c minus b being equal to 3. And we have a minus c here being equal to the constant. A minus c is equal to the constant, which is 1. Now when we continue, we are going to use simultaneous equation to solve for our missing values. So we have a plus b is equal to 0, equation 1. C minus b is equal to 3, our equation 2. Then a minus c is equal to 1, our equation 3. let's use the elimination method. So we can have equation 1 plus equation 2. So a plus c, we are going to get a plus c here. B plus minus b is going to give us 0. So we have a plus c is equal to 3 because 0 plus 3 is also 3. So this becomes equation 4. We can then put this over here. We factorize. We make a the subject and we substitute. Or if we want, let's do this. So we have a is equal to 3 minus c. So we put a is equal to 3 minus c into our third equation. So when we see a, we substitute. We are going to have 3 minus c, that is for a, minus c is equal to 1. Now we obtain minus 2c is equal to 1 minus 3. Then we have negative 2c is equal to negative 2. Our c is negative 2 on negative 2. Therefore, c is equal to positive 1. So since our c is equal to positive 1, we can then substitute to obtain our a here. Then later, since we obtain a, we can also find our b. So put c is equal to 1 into equation 3. So we have a minus 1 is equal to 1. Where we have a is equal to 1 plus 1, then our a is equal to positive 2. So we have a as 2, c as 1. We can now find b. We can put a being equal to 2 into equation 1, where we obtain 2 plus b is equal to 0. Then b is equal to negative 2. Our b now is negative 2. We then substitute it into what we have up here. So therefore, 3x plus 1 on x minus 1, x squared plus 1. When resolved, we obtain a as 2 on x minus 1. We have b as negative 2, so plus our negative 2 here, then x, plus the c which is 1, all over x squared plus 1. And this is how we resolve such rational functions into partial fractions. And this is Florence, the mathematics tutor.